Welcome guys to my YouTube channel Real Science Simple, and let's make the science simple. Currently I am giving lectures on microscopy, and today the topic which I am going to cover is phase contrast microscope. So first of all, we will understand what is the difference between the light microscope and the phase contrast microscope. In case of the light microscope, image is produced when the specimen is absorbing the light. In case of the phase contrast microscope, light absorption is not necessary. Rather, the image is produced on the basis of the phase shift which is created by the phase plate, and which we will discuss in the future slides. In case of the light microscope, condenser annulus and the phase plates are not included in this microscope. In case of the phase contrast microscope, to create the phase shift, the condenser annulus and the phase plates are included. So this is the difference between the light microscope and the phase contrast microscope. So this is the principle of this phase contrast microscope. This is the condenser annular diaphragm. So this diaphragm has a slit, and via these slits the light is passing, and then it is hitting the condenser lens. This condenser lens will condense the light towards the specimen, and as you know, your specimen will be having some places where the refractive index is going to be high or the refractive index is going to be low. Where the refractive index is high, for example, you can say any organelle in the cell or the nucleus, which is a higher refractive index, the light is going to be diffracted, while from the surrounding media the light is not going to be diffracted. So the area that has the higher refractive index, the light is going to be retarded, while the area that has lower refractive index in comparison to these regions, the light is, for example, the cytoplasm, the light is not going to be diffracted or retarded, and that is known as the undeviated light. So one thing which you need to keep in mind is this: certain portion of the cells in your specimen will retard the light, while the others will not retard the light. Now this retarded light and the unretarded light will hit this objective lens, okay, and from this objective lens it will go to the face plate. So this retarded light, there won't be any difference to this retarded light. It will not pass through the face plate, but the unretarded light will pass through this face plate and will retard this light, and that's how the phase shift is going to be created and the image is going to be produced. So let's understand this in a better way. Like this. Suppose this is your light lens, this is the condenser annulus, it has basically the slit. The light will only pass through these slits. So you can say the focused illumination is there. So that is the region the condenser annulus or the annular diaphragm is placed. Then it will hit the condenser lens. From this condenser lens, this condenser lens will condense the light towards the specimen. And now your specimen, if suppose this is your specimen and this is the nucleus and this is your cell which is helping the cytoplasmic region. So this nucleus is having the higher refractive index, and because of this it will retard the light, while this portion which is the cytoplasmic region, liquid region you can say, this has a lower refractive index and it will not retard the light, so it will be the undeviated light. Now the function of the faceplate is what? To create the retardation. Faceplate, what it will do? It will create the retardation in the undeviated light. It will create the retardation in the undeviated light. Okay. So now it will hit the specimen, and from the specimen it will go to the objective lens. Here you can see, and from the objective lens this will go to the faceplate. Okay, this is your, let's say, your faceplate. Faceplate has two regions. One is the retention plate and another region is the gray filter. So this is the retention plate. It will, this retention plate, what it will do? It will retard the light, and this is the gray filter that will absorb the extra light so that you will not get a hazy picture, the extra brightness of your picture. So that is the function of the faceplate. So only the undeviated light will pass through this faceplate, and there is going to be the phase shift because the faceplate will retard that particular light. So you can understand here, this is your faceplate, and this faceplate has let me just highlight this. So this is having, this is the retention plate, this particular region, and this region is a, which is the retention plate, it will retard the undeviated light, and this is the gray filter. This is very important, the gray filter, otherwise you will get a picture that is going to be very bright, and that's what we don't want. So gray light will absorb 30 to 40% of the extra light. So this is the function of the faceplate. Now what is phase shift? So let's understand what is phase shift. So this is your light, which is a surrounded light. You can say the surrounding wave. Okay, and this is the light, this is the region which is the retarded light. Okay, you can see here, this is the retarded, these are the retarded light rays, and these are the unretarded light rays, and these unretarded light rays are only passing through the faceplate. Okay, so the dashes are the retarded light. Now this is the retarded light. So this is going to be same, and this will not pass through your faceplate, will not pass through faceplate. And listen very carefully and don't skip it so that you can understand that. Okay, so it will not pass through the faceplate, it will be like the retarded light on, and one wave is equal to lambda. Okay, this is going to be basically lambda. So this is basically lambda by 2, we can say that, or we can say this is lambda by 4. Okay, now coming to the surrounding, and this is not going to be changed, this particular thing is not going to be changed because it is not going to pass through the faceplate. Now coming to the surrounding wave, means the light that is hitting your cytoplasmic region, for example, let's say, or the lower refractive index region. So now what it will do, the surrounding wave, in case of the positive phase contrast microscope, what positive phase contrast microscope will do, it will advance the light by lambda by 4. And why? Because it has a circular region. The face plate in this positive phase contrast microscope, the circular region, it has one circular region which is very thin, so it will advance the light rays. Okay, so this is the thing. So now what will happen? So it will advance the light rays, means now coming to the yellow point. So this will happen in case of the positive phase contrast, means advance by lambda by 4. You can see here. So this is basically, if you are thinking, this particular region in case of the white light, white color which I am showing, this is the lambda. Definitely this is lambda by 2 and this is lambda by 4. Now this particular peak, now see very carefully, okay, this particular peak is shift by lambda by 4 to here. It is advancement of the lambda by 4. And what happened in that case? In that case it will happen, you will get a destructive interference, because the peak of this particular wave and the value of this particular wave are going to be same. So it will be like this. For example, in case of the destructive interference, what will happen? It is going to be like this. Peak and valley, they are going to be in opposite direction. This is the peak and this is the valley, and that you can see here. Now this is the peak of this wave, yellow colored wave, and this is the valley of this retarded wave. They are in the same phase because they are facing each other. The peak and valley are facing each other. See this is the peak and this is the valley, because this is not going to be changed. This is not passing through the face plate, only this is passing through the face plate. Now this has been advanced by lambda by 4, and because of this, this peak and this valley are in the same phase, you can see here, and therefore it is going to cancel each other and you will be getting the destructive interference, and that is known as the, then in that case what you will get? In case of this, you will get what? The higher refractive index region is going to be darker. Let's make it little bit darker, try to make it darker here. So the higher refractive index will look darker and the lower refractive index is going to look lighter. So let's make it lighter here, okay. So this is going to look lighter. So this is going to be darker region and this is going to be lighter region. So the area that has a higher refractive index will look darker and the area that has a lower refractive index will look lighter in this case. So this is the positive phase contrast microscopy. What happened in case of the negative phase contrast microscopy? So in this particular thing you will get a brighter background and the darker central region. Now coming to the negative phase contrast microscope. In case of the negative phase contrast microscope, what happened? The circular region of the face plate is thick. Circular region of the face plate is thick, and note this point, and therefore the wave will retard by lambda by 4. Okay, again you can see here, this is your surrounding wave, and because this is not going to be changed, only this surrounding wave is going to be passed through the faceplate and is going to be either advanced or retarded. So this is your surrounding wave. Now it has been retarded by lambda by 4. So now its peak has been shifted at this position, and now you see what? The peak of this surrounding wave and the peak of your retarded wave are in the same phase. Can you see that? So we will write it also here. This is the retardation by lambda by 4. And therefore you can see this particular thing, this undeviated light and the deviated light, now they are in the same phase, and because of that you will be getting the constructive interference. Okay, and because of this you will get a opposite results in comparison to the positive faceplate. For example, if your nucleus is having higher refractive index, then it will look brighter, and your cytoplasm will look dark. So the covering part is going to be darker and the middle portion is going to look brighter. So that is the negative phase contrast microscope. I hope it is clear to you now. Okay. Now in the phase contrast microscope there are some artifacts. For example, the shade off effects and the halo effects. And why these artifacts are there? Because whenever the observed intensity does not directly correspond to the optical path difference, that is the refractive index and the thickness values, whenever you are not getting image in the phase contrast microscope which is directly proportional to the refractive index, means if the nucleus is having higher refractive index, it should only look in case of the positive contrast microscope it should look darker, in case of the negative contrast microscope it should look brighter, but this is not always the case. And whenever this happens, there are some artifacts, because the light intensity is not corresponding to the path difference, that is the refractive index and the thickness values. Okay, so now coming to the halo effect. What happened basically in case of the halo effect? If suppose this is your nucleus which is having definitely the higher refractive index, and this is the cytoplasm which is having the lower refractive index. Okay, you can say this one. So this I am saying nucleus. So whenever the light is, there will be the shift from the higher refractive index to the lower refractive index all of a sudden. So some of the light will be, so suppose if this is the nucleus, light is going to be diffracted, but it will not pass through the faceplate. But because there is an overlapping between the undeviated light and the deviated light, so nucleus will deviate the light here. So nucleus will deviate the light, and your cytoplasm will not deviate the light, right? Okay. So this is there is going to be the retardation, and there is no retardation, let's say. And again, because there is a retardation, it will not pass through the faceplate. Okay. But what happened in case of the halo effect, some of the debated light, because at the edges what happened, there is an overlap, because this is the edges and there is a sudden change from the higher refractive index to the lower refractive index. So basically these light rays overlap, as some of the diffracted light or the retarded light will pass through the faceplate, and when it will pass through the faceplate will retard it, and because of that the destructive interference is going to be cancelled. And whenever there is no destructive interference and if there is a constructive interference, you will get the brighter image. So you will get some sort of brightness here. That we are going to discuss here. So at the edges of the objects, let's say the edges of the nucleus, let's consider that. When there is a sharp change in the refractive index, for example from a cell boundary to the surrounding medium, the difference between the direct and the diffracted light is more pronounced. The sharp boundary causes intense interference which results in the bright ring or halo around the edges of the object. This halo is not an actual feature of the object, but it's an optical artifact. Again I am saying, because some of the diffractive light is passing through the faceplate. In theory it should not pass, but because there is an overlapping between the diffracted and the undeviated light, some of the diffracted light, which is also known as the leaky diffracted light, will pass through the faceplate, and when it is passing through the faceplate is retarding it, and now instead of destructive interference you are getting the constructive interference, and that is here. Read it. The absence of the destructive interference between low spatial frequency wavefronts diffracted by the specimen and undeviated light waves produces a localized contrast which is known as the halo surrounding the specimen. So you will get some sort of brightness towards the edges, and how it will look like you can see here. This is your nucleus and you will get some sort of brightness, and this is known as the halo effect. For example, suppose if this is your cell or this is your nucleus, so some sort of brightness around this particular nucleus is the halo effect. This happened because some of the diffracted light is passing through the faceplate. In the actual condition it should not pass, but it is passing because there is a sharp change in the refractive index. So this is known as the halo effect. Now coming to the shade off effect. In case of the shade off effects, what happened? It describes a situation where the homogeneous part of the specimen, if suppose the part is homogeneous, in case of the phase contrast microscope, what will happen? It will not deviate the light, so it should look brighter. That's how they are saying. So are displayed with the same light intensity as the surrounding medium. Although the light passing through these regions experiences a phase shift, only minor diffraction occurs and the angle of scattering is greatly reduced. Therefore, these light waves enter the phase ring like the undeviated light and do not experience any interference. So basically what they are saying, if you have an object and uneven thickness, if suppose your object is having uneven thickness, then in case, or the homogeneous part is having not uneven, I am saying the even thickness or the homogeneous part. So what will it cause? The homogeneous part, you can consider it like a cytoplasm, so it will not deviate the light. Okay, so you will get the brightness in case of the positive contrast microscope. In case of the negative contrast microscope, you will get the darker image. Okay, that's what they are saying. So for example, this is the positive phase contrast microscope. So you can see the brightness here, and that brightness is something like the surrounding medium. Here in case of the negative contrast microscope, this is the darker area and you will get some sort of darkness in the surrounding medium as well. So this is basically in case of the positive phase contrast microscope, and this is basically in case of the negative phase contrast microscope. And this is because your specimen has some sort of homogeneous structure in the middle portion, and then you will get the shade of effects. For example, you can see here, this is the HeLa cell pictures. So you can see the, in case of the positive phase contrast microscope, you can see the brightness here, here and here. In case of the negative phase contrast microscope, you can see the middle portion is darker and the outer portion is also looking darker. So that's how you can see the shade of effects, means there is a gradual sort of shading. Here you can see the, it's a shading, the middle portion is more darker, then there is a gray part, and then again there is a white colored part. Okay, so this is known as the shade of effect. Okay, this is in case of the positive phase contrast microscope. This central region, because this is having the homogeneous structure like the cytoplasm, it will look brighter because it is not deviating the light like the surrounding medium. In case of the negative phase contrast microscope, the central region is homogeneous, so it will look darker like the surrounding medium. Okay. So that's all about this lecture, and if you like the content of my lecture, kindly subscribe my channel. Thank you so much.